All right, so what we are going to be discussing today is second order or RLC. Filters. Okay. And we are going to focus the overwhelming majority of our attention on the two types of filters that we discussed on Monday that can only be realized using second order or higher circuits. So the first one that I want to look at is this guy, where we have an inductor in series with a capacitor in series with a resistor. As always, we will apply our input signal on the left-hand side, take our output signal on the right-hand side of the network. And since we're looking at things in the frequency domain, our inductor looks like J omega L, and our capacitor looks like 1 over J omega C. So what should our transfer function be here? Well, since we're taking the output voltage as the voltage drop over the resistor, it should just be the resistor divided by that series combination. All right. So I am going to write that as H of omega is equal to R divided by R plus J omega L minus 1 over omega C, where I'm lumping the impedances of my inductor and capacitor together into a single impedance. And to be explicitly clear here, I'm also saying that 1 over J is the same thing as negative J, which is where this negative sign comes from when I factor J out in the front. So I've just got it split up into a real part and an imaginary part in the denominator. In order to clear my fraction, I am going to multiply through by a factor of omega C over omega C. And this is going to give me omega RC divided by omega RC plus J omega squared LC minus 1. This is one of a couple of different ways that I can represent this transfer function without having a fraction in it. So this is the one that I'm going to go with because it's the easiest to follow for me. So what we are going to do now is we are going to split this up into its real component and its imaginary component. All right. So I'm going to do that how I've done it the past several times. I'm going to take my original transfer function and I'm going to multiply that transfer function by the complex conjugate of the denominator over the complex conjugate of the denominator. So that's going to look like omega RC minus J omega squared LC minus 1 over omega RC minus J times omega squared LC minus 1. And what will I get? Well, I'll have omega RC quantity squared in the numerator. I'll have a minus J, and then I'll have an omega RC times omega squared LC minus 1 in the numerator of my imaginary part. And then for my denominator, I'm going to have omega RC quantity squared. And then let's see, J times negative J looks like positive 1. So plus omega squared LC minus 1 quantity squared in my denominator. Omega RC squared plus omega squared LC. And I'm just going to scooch this minus J over a smidge here to make it easier to read. So this is my real and imaginary parts. I can now determine my amplitude response, which is always taking the real part squared and the imaginary part squared, adding them together and taking the square root. So that's going to look like omega RC squared divided by omega RC squared plus omega squared LC minus 1, this guy squared, close that off and square it. I add to that negative omega RC omega squared LC minus 1 all over omega RC squared plus omega squared LC minus 1 squared, square that thing, and I'm taking the square root of this whole shebang. And now it's time for a little bit of algebra, right? So for my denominator, that's going to be omega RC squared plus omega squared LC minus 1 squared, and then that whole quantity squared. My numerator is going to look like omega RC to the 4th power plus omega RC squared times omega squared LC minus 1 squared. And I can see here, hopefully, that what I could do is I could factor out an omega RC squared from both of those terms in the numerator, which would leave me with omega RC quantity squared times omega RC quantity squared plus omega squared LC minus 1 quantity squared divided by omega RC squared plus omega squared LC minus 1 squared squared. And this term in the numerator cancels out one of my powers in the denominator, leaving me with omega RC divided by the square root of omega RC squared plus omega squared LC minus 1 squared. Like so. If we were to evaluate this at 0, we would wind up having 0 over the square root of 1, which is 0. If we were to evaluate this at infinity, we would have infinity over, so let's see. So we're going to have an infinity squared plus an infinity squared. Actually, we're going to have an infinity to the 4th power from this guy, right? When we square that guy. So we're going to have infinity over the square root of infinity to the 4th power, which is going to look like 1 over infinity, or 0. So we attenuate low frequency signals and we attenuate high frequency signals. So this must be a band pass filter where our pass band is somewhere between these two extremes. So if I were to plot this response, right here is the magnitude of H as a function of omega. This is 1. This is omega. What I would expect to see would be something like this. Where I have 1 over the square root of 2, like so. I'm going to have a corner frequency omega low. And I'm going to have a second corner frequency omega high. And then in the middle, actually, let me use a different color than red since I want to be not confusing. At our peak, we have our center frequency of omega C. Now, I'm not going to make us derive this because it's a little bit annoying because of the square roots and all that kind of good stuff. But what we will find is that omega low is given by negative R over 2L plus the square root of R over 2L squared plus the square root of one over LC squared. Omega high is positive R over 2L plus the square root of R over 2L squared plus the square root of 1 over LC squared. And our center frequency, omega C, is simply the square root of 1 over LC. So it's extraordinarily similar to what we saw for a series RLC circuit. Because recall, for a series RLC circuit, this is alpha and this is omega naught. So it's practically identical, except that the plus or minus sign occurs out here in front as opposed to inside, telling us what our S1 and S2 values were. So it's very, very similarly related. Now, before we move on from this point, I want to introduce something new to you guys. I think I may have touched on it on Monday, but this distance between omega low and omega high is what's called the bandwidth of the amplifier. For this simple second order filter, if we subtract this guy right here from this guy right here, effectively we're going to have R over 2L plus R over 2L, or twice R over 2L, or just R over L. So the bandwidth of our filter is defined entirely by the resistance and the inductance. And then our center frequency is where our capacitor comes into play. So that effectively, if I asked you to design a bandpass filter, which I'm absolutely going to do, for a specific center frequency and a specific bandwidth, like let's say that we were trying to design a filter to tune into a radio station, right? FM radio stations have center frequencies that occur at like 89.1 megahertz, 89.3 megahertz, 89.5 megahertz, et cetera, et cetera, et cetera, right? So those are all the center frequencies. And then the bandwidth is effectively just the channel separation. So the difference between 89.1 and 89.3, et cetera. So 200, so they have a bandwidth of some number of megahertz. Excuse me, they have center frequencies at some number of megahertz with a bandwidth of 200 kilohertz. So you would design for the center frequency and then using values, commonly accepted values of L and C. And then from there, once you know what L is to give you your center frequency, you can solve for R to set your bandwidth correctly. So it's supposed to be a very straightforward design process. The reason why I am mentioning that specifically to you all is because last quarter, they did not notice how simple it was supposed to be, but in tons and tons of work when it should have just been This equation and this equation give you everything you could possibly need. So I'm giving you guys a leg up. This design project should take longer to write down than it should be to figure out. So anyway. Thank you. Yeah. Still mildly confused as to why they didn't catch it last time. So giving you guys a very strong hint. All right, so here is our magnitude response, our frequency response, or excuse me, our phase response. As per usual, theta as a function of omega is simply the inverse tangent of the imaginary part, which in this case was what? Omega RC times omega squared. All right. Over the real part. This guy cancels this guy. This guy cancels one of these powers. And we are left with the inverse tangent of omega squared LC minus 1 over omega RC. All right. So this was a band pass filter. Okay. So when we have that series RLC combination, if we take the voltage drop over the resistor, we see a band pass filter response. So now let's do the opposite. Here is the in, here is the out, okay? So in this instance, we are taking the voltage drop over both the inductor and the capacitor in series, okay? So when we had an RL circuit, what happened when we took the voltage drop over the inductor? We got a high pass filter. When we had an RC circuit, what happened when we took the voltage drop over the capacitor? We had a low pass filter. So it stands to reason that this is going to be some combination of a low pass filter and a high pass filter, which we call a band stop filter. Okay. So in this case, we are going to have in the numerator J times omega L minus 1 over omega C. And then the numerator, the denominator, we're going to have exactly what we had previously, R plus J omega L minus 1 over omega C. And if we multiply through by omega c over omega c, we wind up getting j omega squared LC minus 1 divided by omega RC plus j omega squared LC minus 1. So that's our simplified form of our transfer function where we don't have any pesky fractions inside of fractions. And we're going to take that bed and run with it to develop our, to split it up into its real and imaginary constituent parts, and then use that to find our magnitude response and our phase response. All right, so let's write this down. We're going to multiply this guy by the complex conjugate of the denominator over the complex conjugate of the denominator. That's going to look like omega RC minus j omega squared LC minus 1 times omega RC minus j omega squared LC minus 1, which will look like omega RC squared plus omega squared LC minus 1 squared in our denominators. And in the numerator, we're going to have a real part that is omega squared LC minus 1 quantity squared, because we have j times negative j giving us positive 1. And in the imaginary part, we have j omega RC times omega squared LC minus 1, and we have a plus sign. Algebra checkout. All right. So from here, we obviously can determine our magnitude and phase response. So our magnitude response is going to be the real part squared. So omega squared LC minus 1 squared over omega RC squared plus omega squared LC minus 1 squared, this whole thing squared. Our imaginary part, omega RC times omega squared LC minus 1 omega RC squared plus omega LC minus, omega squared LC minus 1 squared, this whole thing squared. And that's going to give us a denominator. Omega RC squared plus omega squared LC minus 1 squared, square that whole thing. Up here in the numerator, we are going to have omega squared LC minus 1 squared times omega RC squared plus omega squared LC minus 1 squared, like so, where I went ahead and factored out the common thing. Obviously, when we square this square, we're going to have a fourth power of this guy on the left. When we square this, we're going to have it squared. Take that squared out of both sides, giving us this guy. And finally, that is going to give us omega squared LC minus 1 over the square root of omega RC squared plus omega squared LC minus 1 squared. Where at 0, so at 0, this is actually going to give us -1, and it's because of the sign convention thing here. It's really not going to particularly matter. But we're going to have, so 0 minus 1, which is -1, and then down here, we're going to have 1 squared. So effectively, we're going to pass signals, but we're also going to invert their sign. So I'm going to call this 1 in parentheses because it's 1, just the sign gets flipped. At very high frequencies, we're going to wind up having infinity squared over the square root of infinity to the fourth power, infinity squared over infinity squared, or 1. And so we can see that we pass low frequency signals, we pass high frequency signals. And so this is a band stop filter because it's in that intermediate range where signals start getting attenuated. Plotting this, we should see something of the form, let's see, let's call this 1. Something like this, or if this corresponds to 1 over root 2. Here is where omega low occurs. Here's omega high. And then directly at the center, we have omega C. Now, one thing that I do want to point out is that if omega low and omega high aren't far enough apart, omega C is still going to be at the minimum value of this, but we might not necessarily hit 0. We're going to see a dip, but if these guys are too close together, the dip isn't going to extend all the way down to completely attenuating the signal. Yes.
So does the track between the
Not particularly. So
yeah,
generally speaking, exactly right. It's a ratio. So there's another way to effectively look at this that'll make the sign work out right. Yes, it's just because of the way that we're looking at it, that we're getting that negative value in the when we evaluate it at 0. Not to get too wild or weird, but we could force this to work by looking at negative frequencies, which don't exist, but the negative frequencies are how circuits behave at negative frequencies are a very important part of their behavior in determining whether or not a system is stable or unstable and all that kind of good stuff, which is well beyond the scope of this class. But that's another way to fudge the math and make it come out in our favor. But this is reasonable enough. So because we have a simple RLC circuit, omega low, omega high, and omega C, as well as our bandwidth for this circuit, are going to be literally identical to what we saw for our band pass filter. It's just that we're taking the voltage drop over two different elements, or the opposite of what we did before, that we get the opposite response. So just for the sake of argument, I'll write all that stuff down again, but it is literally nothing different than what we did a few minutes ago. Omega low was negative R over 2L plus the square root of R over 2L squared plus square root of 1 over LC squared. Omega high is positive R over 2L plus the square root of R over 2L squared plus the square root of 1 over LC squared. And omega C is the square root of 1 over LC. And our bandwidth, and I'm putting this in quotation marks because this actually represents the range of frequencies that we attenuate as opposed to the range of frequencies that we pass in our bandstop filter. They're still going to come out to be exactly R over S. This is the width of the notch as opposed to the width of the passband in this case. And finally here, our phase response theta as a function of omega will be the inverse tangent of the imaginary part, which is here, omega RC. There. I'm technically dropping the denominators from both the real and the imaginary part because they're the same thing and they're going to wind up canceling each other out anyway. Oh, and this should be squared so that this cancels one of these powers. And we have the inverse tangent of omega RC over omega squared LC. All right, so very, very briefly, and by that, I mean, I'm not going to actually do any of the math involved in finding the magnitude response or phase response. We're going to talk about second order low pass filters and second order high pass filters. Okay. So if we have our RLC circuit, and we take the voltage drop only across the capacitor, we have a low pass filter. I'm just going to abbreviate that as LPF with a transfer function of 1 over 1 plus omega squared LC plus j omega RC. And we'll have a cutoff frequency omega c of 1 over the square root of LC. And if instead we take the voltage drop over the inductor as opposed to the capacitor, sorry, that should be Vn on the left-hand side. Getting ahead of myself. We have a high-pass filter with a transfer function of h of omega is equal to omega squared LC over 1 plus omega squared LC plus j omega RC. And again, we have a cutoff frequency omega c of 1 over root S. All right, so that is enough. Yes, Roger. All right, so that's all I wanted to talk about for filters in this class, just to introduce you guys to the concepts, all that kind of good stuff. I'm going to have you do a design problem, which I get to go up to my office in a couple of minutes. I will upload. Designing a band pass filter that would be capable of tuning into Louisiana Tech's radio station. I'm going to have you simulate that filter in LT Spice. So actually, I didn't bring a mouse. I might just put up a video of me doing a quick simulation for an AC sweep circuit to show you how to do that kind of simulation. But effectively, all it is you're using the AC sweep analysis as opposed to the transient analysis, which we use for our transient analysis of RLC circuits, or as opposed to the DC sweep that we did earlier on. Typically speaking, you would do a decade sweep. 1,000 points per decade would be appropriate. And then let's see, your starting frequency. So if we're trying to hit something in the ballpark of 100 gigahertz, run it from, 100 megahertz, you would start your sweep somewhere in the ballpark of 1 hertz and end it somewhere in the ballpark of 1 gigahertz. And that should give you a good picture of everything. Those would be the settings you'd use. Yes. Yeah.
Could you also show us how to set up like cycle?
Okay, so I can.
We need to use that for testing.
You don't. So instead, let me pull up LT Spice here real quick. I don't want to. No, I don't have a mouse, so it's going to be a huge pain in my butt. Let me. Let's see. Yeah, let's see. Yeah, these cables out of the way. All right, so the first thing is I need to get rid of that. All right, so setting up a voltage source. Just right click the voltage source to get the, pull up the advanced tab. We're going to completely ignore the left-hand side here. What we're going to do is this bit, the small signal AC analysis. And we are going to intentionally choose an AC amplitude of 1. So what that's doing is it's giving us a source that has an amplitude of 1 volt over all frequencies of interest. The reason why I'm doing that specifically is because if we choose our AC amplitude to be 1 volt, then V out is our transfer function because we're just taking V out over 1 over all frequencies.
If we want to use this for like checking our homework, is the AC out?
There is no homework for filter stuff.
Oh, okay. I mean for like with the phasers and stuff.
For that, you would need to actually set a sine function up. And then you would have to specifically measure your phase angle with respect to 0 and your amplitude and all that kind of stuff. It can be done, but it's a huge pain in the ass to do with LT Spice, which is why I didn't do it. Okay. So I'm just drawing a box around this for now. All right, somebody give me a resistor value. All right, somebody give me a capacitor value. No, it doesn't matter. And I'm going to call this node V out. All right. So let's run a quick simulation here. So I want to do an AC analysis, decade sweep, 1,000 points per decade. And just because I'm not entirely sure where our corner frequency is, I'm going to run this from 1 millihertz to 1 gigahertz. And I'm going to assume it's probably somewhere in that range. If I plot V out, this is literally the same thing as my transfer function. Okay. So this solid line is my magnitude, exactly right. And the dashed line here is my phase response. All right. So we can see that our corner frequency, or where this guy starts to bend, is somewhere in the ballpark of 1 hertz. How we would do this more specifically, measure things, is if we click on this, we get a slider that we can use. So because we are using passive filters, our voltage gain literally can never be larger than 1, which corresponds to 0 decibels, okay? So our cutoff frequency is then going to be whatever frequency our magnitude hits -3 decibels. So let me find this thing again. We just slide this over. That's pretty close. So our 3 dB cutoff frequency is going to be somewhere very close to 3.16 hertz. That's how we can find it. So I want you to do something similar to this, except with an RLC filter circuit, where you're going to have a band pass response, and you should see that at like 89.0 megahertz, you're at -3 dB, and at 89.2 megahertz, you're at -3 dB. And at 89.1 megahertz, you're at 0 dB. If you've matched that, you're good. Your graph can look significantly different depending on what frequency range you're looking over. And so what I mean by that is it might look really steep if you're looking at a very wide frequency range, or it might look like a very subtle peak if you're narrowed in very close to the frequency range of interest. So if you and your peers don't get the exact same looking graph, it might be just because you set your boundaries of your simulation up differently. But as long as you're hitting -3 dB at the center frequency minus half the bandwidth, and you're hitting -3 dB at the center frequency plus half the bandwidth, you've got it right.